Good day, everybody. Today we're going to look at the different optimization properties that different methods of apportionment give for a fixed, country's population, and then you have the population for each state. You can apportion in different ways. Well, those methods of apportionment actually optimize different things, and so we're going to look at that. For what follows, we'll use the notation that P will be the country's population. That's around 331 million for the 2020 census. S will be the number of seats for the country. So that's 435 in all the apportionments I look at. I look at 1990 and 2020. And then for state K, PK will be its population, and SK will be the number of seats it gets for a given apportionment. Okay, so let's take a look. Then here is 2020's official census population. I've got it twice actually. Say, look over here. Again, total around 331 million. So this is from the 2020 census, and so we can use different methods of apportionment. Of course, the one used is Huntington Hill, so I've got that. But I can compare if I look at Hamilton's method of apportionment, or Webster, or Jefferson, or Adams, or Dean, rounding by the harmonic mean. And I threw in some extras where I rounded using different means, like the Gauss arithmetic geometric mean. I rounded that way. I rounded by the Huronian mean. Got this apportionment. I rounded by the root mean square. I also rounded by the centroidal mean. And for this population, they came out the same, the apportionment. The root mean square and the centroidal mean came out the same. The Huronian and Gauss arithmetic geometric mean came out the same. Also looked at the contraharmonic mean. Anyway, so here we go. And we've got these different apportionments. So the first optimization property I want to look at is if you just divide each state's population, like so there's Alabama, divide it by how many seats it would receive depending on the method. So just about every method gave it 7 seats. So if you divide this 5 million by the 7, you get this number. So a lot of agreement there. Jefferson, though, would have only given Alabama 6 seats if we use that apportionment. And so if you divide that population by 6, you get this number. So this represents how many people per seat on average that state has. So if you're a state, you want that value low, because otherwise each congressperson is representing more people, and it kind of means you have less representation. All right, but I mean, some states are going to be above, some states are going to be below. Like, let's look at Huntington Hill. It gave 920 million for Idaho. That's the people per seat. Whereas some other methods gave it maybe 600,000 people per seat. Anyway, so if you do this with each method in each state, Adams will be the state which minimizes that maximum value. So the maximum value with Adams is 801,000. That's the smallest max if you go column by column. And if you find the average, Adams will also minimize that. And that seems like a nice property to have. You want to minimize how many people per seat are represented for each state. So it seems like a nice property. But Adams' method is not going to be one used. We already know it violates the quota, lower quota. It's more likely for large states. So like California, it should have gotten 51 or 52. 52 seems pretty reasonable. But it only gets 50 with Adams. And then Texas, another large state, it should have gotten maybe 38, but instead it only got 37 seats. So there's that lower quota violation. And that's part of the problem, is with large states, it's not such a big deal. Actually, Florida, another large state, it got under its lower quota as well. And we'll see. Let me first just look at another thing that Adams optimizes. So people per seat, keeping that low, and also how much you're over. So the country's average should be 760,000, 761, 169. So that's the country's average. So we'll only count if you're above that. If you only count if you're above that, I get this next quantity. Right, so we can see all the states now. So if these numbers are below the standard deviation, 761, just kind of 0, but if it's above, like Arizona, in fact, then a big one's like California, so highlight California there. So, almost everybody wanted to give California 52. Jefferson actually gave it 54, but Adams only gave it 50. So California is over the standard deviation. And it's not too much over, just 30,000. Anyway, so Adams will optimize this sum then as well. If you're over, you count it. If you're not over, you just count it as 0, and then that sum. And so one of the things I noticed was, well, that's because California only counts as one unit. It's one state. So Adams takes a hit on California of that 30,000, but it only counts once because California is just one state. If you multiply these quantities by how many seats they're getting, right? Because really California, well, with Adams' method would get 50 seats, and with others 52 seats. But if I multiply this number by 50, because this is going to happen then for 50 representatives. So I got to keep going here. Then, so if you multiply this by the Adams gave California 50, so I get the 1,500,000 instead. Then that seems a little more real, what's going on, right? You should take a bigger hit if you go over one state, rather than just do it as by one state. As I said, do it by, well, how many times does it happen? So this is kind of happening 50 times for Adams, and so on. But so if you do this for every state, then Hamilton will optimize that. So it's the number of seats for each state times that maximum of how much you're over the standard divisor. Let me look at some other years. I've got 1990 here. Here's the 1990 population. Again, we've got these other methods. If I look at them all, again, the centroidal mean and the root mean square were the same. I didn't do the contraharmonic mean here. But so there, again, there is one more mean above the root mean square that's under Jefferson, contraharmonic, but anyway. Also, Gauss and the Huronian mean are the same again. So I won't show them just to save a little column space. So what do we got? We've got our different apportionments then, again with the main methods, Huntington, Hill, Webster, Dean, Jefferson, Adams, and Hamilton. And now these are all distinct this time. Right? So you can see Hamilton is different than both Huntington, Hill, and Webster, and all these methods give different results. So if we look at whoops, I went too far. The people per seat. Here's the population. So just divide each state's population by how many seats you get for each method. Then Adams will minimize that. It'll minimize the maximum and the average. And then if you only count how much you're over the standard deviation, which in 1990 was 572,000-ish, then look a little bit here. Right, so how much you're over that standard deviation, if you count that, then again, Adams will minimize that. But if you multiply each state by how many seats you would get from that method, then Hamilton will now optimize that. So that's the smallest number there. And one more look at a population. This is the 2020, not real population, but I was trying to approximate it using some census data year by year. And of course, I didn't do it exact. So this is an incorrect population here. You can see the total's not right. I had 329, which is really 331. And my apportionment wasn't right. But I thought it was interesting that the Gauss was different than Huntington Hill and Webster. The Gauss, so if you round by the arithmetic geometric mean, you get a different result. And of course, this means in between these two. So I want to do some comparisons with this as well, even though this census data, hypothetical, didn't actually happen. But you can still do the math and compare things. So again, people per seat, divide each population by number of seats given by the method. Adams will optimize that. Only count how much you're over. The standard divisor for this hypothetical is 758. Adams minimizes. But if you multiply by how many seats you get, then Hamilton will optimize. Now, Hamilton and Webster gave the same apportionment in this hypothetical. So I didn't list Hamilton. I put Gauss in this spot. But so when I put Webster, it's the same as Hamilton. So that's the best of being over people per seat. Well, what else can we optimize? So if we go to 2020 again, actual, I can look at just the absolute difference. So if you take the people per seat, so we already computed that. Let's go back to the end here. So if you take the people per seat, and then here we only counted if you're over, but instead now we're going to count how much you're off the standard divisor. So just take the absolute value difference. So if you're over, you count it. If you're under, you also count it. Right? So right here we didn't count it if you were under. But here I'm checking just the absolute difference of people per seat calculated over there minus the ideal, or what every state should have, the country's average anyway. So how much you're off the country's average. Dean will minimize that. So there we go. You can see it there. If I go to 1990, so again, people per seat minus the standard divisor. We can compare and see if I go a little bit over. Right, so there's that 7906. But then again, here we only counted if you're over, but now we're counting absolute value if you're over or under. So Dean minimizes that. And the hypothetical, it'll minimize as well. So Dean. So Gauss didn't do it. Dean does. So let's see, what other properties? Let's go back to 2020 actual. This is if you multiply people per seat minus the standard divisor, or the average for the country. So how much you're off from the average of the country. But now, again, each state only counted once. So if you multiply this by how many seats there are, then Hamilton will win. Right, so you just take this quantity. So again, California, I mean, that's a 77. Let's maybe look at, say, Texas or something. Oops. So this is over the ideal just by a mere 6,000, and then you multiply that by how many seats you gave out. So Hamilton would give that state, Texas, 38. But Dean, which minimized, if you don't multiply by number of seats for each state, now is no longer the minimum. It's Hamilton. If that makes sense. Let's just maybe look at a couple more years if it didn't. So again, if I look at people per seat minus the ideal, Dean wins. But if you now count how many times this happened, so multiply each of these by how many seats you gave out for each state for the given apportionment, Hamilton will now have the minimum. Webster was second. Where's Dean? Dean, and then Huntington Hill, and then Dean. So Dean, which minimizes if you count each state as only one unit, is now further behind. And then for the hypothetical, again, people per seat minus the ideal, Dean wins. Multiply by how many states you got. Multiply each of these by how many times it happened. So Hamilton wins, but Webster has the same apportionment. Let's see. Gauss did better than Huntington Hill. So again, this is the one where Gauss was different than Huntington Hill. Anyway, so for whatever that's worth. So now, if we look at the inverse of, instead of people per seat, we're going to look at seats per person. So this is like, what share of a congressperson does each person have? So for example, I mean, it's a pretty small number. So these are all in scientific notation, but I'll just make up a number. Like if one state had 10 people, then each person would have 0.1 of a congressman or congressperson. But if then there were another state with 100, then each person would have 0.01. And so you don't want to overdo it. Like, let's look like, well, Jefferson goes over. I guess scientific, so we can't really see too well, but Jefferson's going to minimize this. And it is something you kind of want to minimize. I mean, it's one thing if you're in California and you get overrepresented, which you would with Jefferson's method. But you know, if you're not in California, you're saying, well, that's not fair. They're overrepresented there. They have more of a share of each congressperson in their state. So you kind of want that near the ideal as well. Anyway, Jefferson will minimize that, and it will minimize if you only count how much you're over. Right, so how much are you over? This is, of course, 1 over the standard divisor, so it's a really real small number. So again, in California, they're overrepresented, so they're over that, but that only counts as one state, so it's okay to overrepresent these people, and all these other states won't be overrepresented. But if you multiply how many people were overrepresented, so multiply this quantity by the number of people, Hamilton will win. Right? So with Jefferson, you can kind of overrepresent California, but only counts once. But now if you say, well, there's this many people, I forget, there's 40 million roughly people in California, then taking that into account, Hamilton will win. And again, Hamilton and Webster have the same apportionment here, but if we compare to 1990, so again, here's the flip. Seats per people, Jefferson will minimize. How much you're over the ideal, Jefferson will minimize. But multiply that by how many people are in each state that's overrepresented. Hamilton will minimize that. So multiply by the number of people. And Continuing, let's go back to the actual 2020. So this is similar to Dean's. If you just do seats per person minus the ideal. So here's the ideal. This number would just be 1 over the standard divisor. So how far away, so not just how much you're over, but again, just like what we did before, this is only if you're over. Of course, this is here multiplied by number of people, but how much you're over, and then 0 if you're under. But now, just how far away are you? So if you're over or under, you count it. And just that difference. Webster will minimize that. So you want to, ideally, you should be right at this fraction. Anyway, so Webster minimizes that. But again, if you multiply by the number of people, Hamilton will minimize that. But for this apportionment, Hamilton and Webster are the same. If I go to 1990, where Webster and Hamilton are different, then there's the difference there. Webster wins out. It's got the, what was that, the max? There's more likely to be a tie in the max, especially if there's like a real small state, I think, where you're forced into a certain apportionment, because every state has to get at least 1. But then the average, it's a little hard to see, but Webster has the smallest average of how far away you are from the ideal S over P. So Webster minimizes that. But if you multiply each state by the number of people in that state, Hamilton will now minimize that. And again, with the hypothetical, where Gauss is in there, the new one, it won't have any optimization. Oops, so there's seats per people. Jefferson minimizes how much you're over the ideal. And if you multiply by the number of people, Hamilton minimizes that. Here, if you count just how much you're over or under, in other words, absolute value, Webster will minimize that, and it beat out Gauss. A little hard to see, but there you go, you can see a little smaller. And if you multiply by the number of people in each state, then Hamilton minimizes that. But Hamilton and Webster have the same apportionment with this hypothetical. All right, so that's almost it. I did look at a couple other things, just trying to see, because we use Huntington Hill and it hasn't minimized anything yet. So I was searching for things that it minimized. Well, if you take the product of these magnitude differences, Huntington Hill seemed to minimize that. So, right, so Dean minimized the people per seat minus the ideal part. Webster minimizes this. If I multiply them together, Huntington Hill seemed to minimize that. I also multiplied, and of course this was no surprise then, that if you multiply by the number of seats and the number of people, Hamilton minimized each of those separately, so of course it'll minimize that product. And you can just verify year by year. So again, for this apportionment, Huntington Hill minimizes this product for whatever that's worth. You could think of it as a balance. Well, you'd like to minimize this, you'd like to minimize that. Well, if I minimize the product, that's a balance between the two. Although that's never brought up, so I never saw it in any literature. And I'll show what they talk about that Huntington Hill minimizes in a second here. But again, there's, for this method, and Gauss being close by, but close but no cigar. Gauss actually beat Webster there. All right. So let's talk about what is really talked about with the Huntington Hill method, and that's, if we look at these pairwise properties, and you can read the original article, apportionment and what you want to minimize. He was into relative difference, saying that's the important thing, like 250,005 is 5 more than 250,000. 15 is 5 more than 10, but relatively speaking, you know, the 15 and 10 seem to be more important. So if you talk about relative difference and go into things like that, that's what this article is about. I'll have a link where you can get to it. You just get the full text PDF. It's pretty readable. And again, these are some of the properties that the divisor methods minimize. We looked at those already. But they talk about pairwise. So let's look at that. So we'll start with Idaho and Minnesota and compare it to Huntington Hill. Dean's method versus Huntington Hill, because they're the same everywhere else for all the other states, but they're only different in Idaho and Minnesota. So with Huntington Hill, Idaho gets 2, with Dean, Idaho gets 3, and Minnesota gets 8 with Huntington Hill, and Minnesota gets 7 with the Dean running by the harmonic mean. So let's look at what we've got. Here's the Huntington Hill method. You get 8 and 2 for those two states. Here's their population, and then divided by the 8, you get your people per seat. And similarly with Idaho, people per seat. Well, I can take the absolute difference, and that's 206,000, almost 207,000 this way. And then compared to Dean, if I take the people, divide by the number of seats, I get people per seat for each state. Take the absolute difference, I get 201,000. So again, Dean minimizes that. But what we want to do is minimize this relative difference. So the relative difference is, well, you take the absolute difference and you actually divide by the smaller of the two numbers. In this case, the people per seat, the smaller number would be Minnesota's number. So that's the relative difference then. This absolute difference divided by that people per seat. And so that gives me this number. If I do it with Dean, take its absolute difference divided by the smaller of the two numbers, the 613, roughly, I get this bottom number. And it's a bigger number, so it has a bigger relative difference. Okay, so Dean has a smaller absolute difference, but the bigger relative difference. I also divided that absolute difference by the other state's population, the bigger state, so of course that's a smaller number, and divide by this absolute difference by the bigger state's people per seat, got this value. And of course this one's bigger as well, maybe not of course, but also the average for Huntington Hill is going to be small. Each of these numbers is smaller than those numbers respectively. This, which we would consider the relative difference, is smaller, and then this other one is smaller. So the average is smaller. So that's what Huntington Hill is going to minimize, this relative difference. Let's see it again. I did it with Webster as well. Now here there's a few differences. By the way, Hamilton's the same, but regardless. So what do we got? We've got Montana is different. 2 with Huntington Hill, 1 with Webster. And Rhode Island would get 2 as opposed to 1 with Webster. And these other two states would get more, New York and Ohio. So if I want to compare, well, we'll look at them here. There's a lot of comparisons to do. Look at them all simultaneously. Here we go. So New York gets 26 and Montana 2 with Huntington Hill. But with Webster, New York gets 27 and Montana gets 1. So if you compute the people per seat, so you take the state's population, divide by the number of seats given by the method. So I divide by 26 here, I divide by 27 here, so that's smaller. Montana gets 2, so if I divide by 2, I divide by 1. Then this is the relative difference to each other. I won't do the absolute difference. absolute difference would be the numerator. So how different are these people per seat to each other? Subtract them, take the absolute value, divide by the smaller number. And the smaller number is this one, the 0.43. So it's actually going to be the bigger of these two decimals here. So this value right here is going to be the relative difference. And then over here, if I divide by the smaller, it's this one. So Huntington Hill had a smaller relative difference. And then I also find the relative difference with respect to the bigger state's population, well, the state with the bigger people per seat. You get this value and that value. And again, that one's smaller. So if pairwise they're smaller, then of course their average is smaller as well. So Huntington Hill is going to win that battle each time. If you take the bigger, it's going to be smaller than that bigger. And the smaller will be smaller than its smaller. Okay, so just find the people per seat. And then for the relative difference, you find the absolute value of the difference, divide by the smaller number. That's the official relative difference. So that'd be this one. And do it with the other apportionment. So absolute value of the difference of people per seat, divide by the smaller people per seat. So would that be this one? Huntington Hill will always win that. It'll have a better average as well from any apportionment. Again, here I only did it with Webster. Interestingly though, something similar, Webster does win, and it's a relative difference. So if you compute the people per seat for each state, and we did that, but I'm only going to now compare where they're different. So again, these are where they're different. Instead of subtracting one state to another, right? So if I were to make the switch, so if I were to switch from Huntington Hill to Webster, the relative difference would go up. And that's what they say is so great. For some reason, it's really just a preference, to be honest. In effect, so here's another preference that's a relative difference. If you compare your people per seat, how far away are you from the ideal or the average for the country, the standard divisor? So this people per seat, how far away are you from the people per seat for the country? That's 761,000-ish. And then the relative difference, so then I divide by that state's population. Divide by that state's people per seat. And I do that for both states. Webster is actually going to win this. So these are the two values I get. And well, if I see how far away am I from the ideal, this people per seat from the ideal, relatively speaking. So this is relatively speaking. Then again, Webster is smaller. And both these values are smaller than that. And so of course its average is smaller. And you can do that for each of these comparisons, right? So where they're different. So there's different ways if you just wanted to do one switch. You could have done the one switch this way or that way and so on. So just find people per seat, compare it to the standard divisor or the average for the country. How far away are you from that? Relatively speaking, you're closer, relatively speaking, with Webster. And this one's easy. It's not easy to do a full sum with this pairwise comparison with the Huntington Hill, but it's easy to do the people per seat minus the ideal, because right? Huntington Hill can only do a pairwise comparison, whereas Webster, you can do kind of a global, just how far in people per seat are you from the ideal, relatively speaking, so divided by your state's people per seat. And Webster will always win that. If I go to 1990, that's all I did here. The people per seat for each state minus the ideal, relatively speaking, so divided by the people per seat for each state, Webster wins. It beats Hamilton And actually you can show that it wins mathematically. And again, if I do the hypothetical, because Gauss was in between Webster and Huntington Hill. So again, I did the relative difference, Huntington Hill to Webster, and Huntington Hill won out. This is technically the relative difference. It's smaller with Huntington Hill. And the average, you can see Huntington Hill wins that. And if I compare Huntington Hill to the Gauss arithmetic geometric mean, it won as well. So right, so there was a difference there, which just testing. So again, state's population, number of seats given by that apportionment, your people per seat. You can compare the relative difference, just take the absolute value of the difference, divide by the smaller state's population, and you get that, which is smaller than this rounding. And same for the average. But if I compare to the ideal, so you take each state's population, and so here, just a quick look, that for this hypothetical, this people per seat for the country would have been 758,000. So take each state's population minus that ideal, or actually I did the ideal minus the state's population, divided by the state's population, you get this relative difference. So again, it's a relative difference, and Webster wins that. So there we go. Beats out Gauss, arithmetic geometric mean. Again, so a summary of kind of what we saw, a little hard to see, but Adams minimizes this. We didn't quite look at it this way, because again, this is pairwise comparison, but there's that max. So I looked at these two, the max of P over S, Adams minimized, and how much you're over the ideal. Dean minimizes this absolute difference of people per seat, and some similar things. So this is pairwise, but also to the ideal, as we'll see. Here's what Huntington Hill minimizes. It minimizes a few other flipped fractions, but it pretty much, this is what we saw. Webster minimizes this S over P instead from the ideal. And again, which means it minimizes P over S, relatively speaking. And let's see, and then there's Jefferson. We looked at these two, the max of S over P and this, where you only count how much you're over. And then Hamilton, when you multiply P over S by how many seats each state gets, and that seems like a nice thing to minimize, to be honest, because maybe you should count California as more than one and so forth. And S over P times the state's population. Just for the math, I had to do this myself because only pairwise comparisons were shown, but P over S pairwise, if that's what you want to minimize, I show it's equivalent to minimizing P over S to the ideal, so this would be Dean, and that's basically by the triangle inequality, and I didn't do the full proof, but you can kind of see that if you're going to take one seat from a state and give it to another state, then one should have been given too many and one too little, type of thing. Or one should be at its upper quota, one should be at its lower quota. If both states were at their lower quota, and then you take away one seat from one of those states and give it to another, then that state that you took it from will now be below its lower quota. So assuming there won't be a quota violation, you will only give seats where the states are on opposite sides of the average, right? Because to get on one side of the average, let's see, I look at, if you're greater than P over S, you had to divide by a smaller number. than S, or well, then the its true quota. It's true quota. You had to divide. If you divide by its actual true quota, you would land exactly at P over S. But you must be dividing by a smaller number. In other words, it's lower quota if you're on the right. And so both states won't be on the right. One state will be on the left. This state would have been given its upper quota. Again, if you divide pk by the exact quota, you would be right here. But if you divide by the upper quota, you'll be to the left. You're dividing by a bigger number, so you get a smaller fraction. Anyway, so assuming they're on opposite sides, then you can kind of do the triangle inequality. And so if you minimize pairwise, you minimize this global thing that I did with the sum. And similarly with the S over P, so Webster does this pairwise, so it'll do this globally, and that's what we saw with the Excel, because it's hard to do this sum. I don't know, you can't really do it, so, but it's easy to do this sum. But the relatively speaking, so again, it's flipped. So it's S over P is Webster in absolute. But let's see. If I want to see relatively speaking PK over SK minus the ideal, relatively speaking, let's see. To minimizing this. So just divide this fraction into the numerator. So of course you get 1 and then minus P over S divided by that. So I just took this denominator. All these fractions are positive. So I brought it inside the absolute value. And of course you get 1 minus then this over this. And then you can flip. Got all the little steps here. And then you can think of it as instead SK over PK divided by S over P. And then get a common denominator, S over P divide by S over P. Take this denominator out. It's actually a constant. So you can pull it out and then might as well flip again. It's P over S. So minimizing this is equivalent to minimizing this sum. And this is just a constant out here. But we know Webster minimizes this sum. So Webster will minimize this sum, as we saw. And then this is what it's advertised that Hamilton minimizes. And again, with some math. Actually, the second one's easier. Let's look at the second one. The second one, you just divide out pk, or factor out pk, then you get this sk over pk minus s over p. Right? So if you factor out pk, you can see this. So if Webster, or if Hamilton minimizes this, it'll minimize this, as I showed, or we saw. A little harder. If instead we factor out s over p, so factor that out, then here I need a p over s, right? Just think if you distribute, get that. And then now pull out an sk, and well, that's it. Again, outside here is a constant. So if you minimize this, then you minimize this, and minimizing this is done by Hamilton. So as promised. So those are the properties. And again, one last look. If you go to the web pages, it's easy to find these pairwise things, which I converted from pairwise to global. Hamilton, again, was this, as I had, and with Q equal 1 was the only one I cared about. So this is a long video, but something to think about. Again, we do this apportionment. There's lots of possibilities. Look at them all again. Let's go to the actual. For 2020, 1990 had, I think, more possibilities, but why is Huntington Hill used? It's that relative difference. But Webster has a relative difference. All these other optimization properties count each state as one. Maybe you should count the number of seats in each state. right? How many times is it happening? So if you give California a hit, it's sort of happening, 52 times or 50 times or whatever. Anyway, they sometimes say Huntington Hill kind of favors small states because of where you round. If you're rounding below 0.5, you're more likely you're going to end up helping smaller states because you often have to divide by a bigger number, which hurts bigger states. If I go real quick again, I think I mentioned this, but in 1990, at least compared to Hamilton, it was a smaller state that gained a seat. Where was it? And a bigger state, not. Webster versus Hamilton. But maybe you can make an argument for Webster, or just for fun, if you're a crazy mathematician person, you can, the mean that is in between the two, Webster and Huntington Hill, it seems that Gauss will actually more likely be like Huntington Hill because that mean is closer that way. Again, one last look at some of the means. With Adams, you always round to the min, and Jefferson, you round to the max. Otherwise, you got this harmonic mean, geometric mean, Gauss arithmetic, geometric mean, Aronian mean, arithmetic mean, centroidal mean, root mean square, contraharmonic mean. And these numbers get bigger as you go to the right, except I put the max just right there. So if you want the mean of two numbers, there's many ways to do that. It's got those properties. All right, time to end the video. Hope you enjoyed, and if you're from New York or Ohio, maybe try and start a fuss, see if you can change the apportionment. There's usually a battle, whether it was fair or not. All right, have a good day.